Good day, ma'am. Today we will talk about Dijkstra's algorithm and why it is important for finding the shortest path between 2 points in a graph. But before that, I would like to introduce myself. I am Jesseboy B. Lapus.
And I am Mike Angelo Artisuno.
I am Ken Archie Coro.
My name is Kevin Okaidik.
I'm Ronnie C. Nongayan.
So, Dijkstra's algorithm is named after computer scientist Edgar Y. Dijkstra. It is used in many real-life applications like GPS, navigation, and network routing. Understanding this algorithm also helps us learn about graph theory, which explains how different points or nodes are connected by lines or edges. By learning Dijkstra algorithm, we can find the best way to travel between points in network. Next is let's see how Dijkstra algorithm works. And works. It's a basic method for finding the shortest path between points in a graph. The algorithm uses a priority queue to keep track of the shortest distance from the starting point. It repeatedly picks the point with the shortest distance and updates the distance to its neighbors. This process continues until the shortest path to all points is found. Dijkstra algorithm works well with graphs that have positive weights, ensuring that we find the best path every time.
Time complexity, big annotation, and the discussion. Now let's talk about the complexity of the Dijkstra's algorithm. The time complexity is written as as O B plus E or log B, which B stands for the number of vertices and E is the number of edges. This notation help us understand how the algorithm performance changes as the graph grows. In simple terms, the Dijkstra's algorithm find the shortest path by looking for the smallest weights between points. It works very well with the graphs that have positive weights and non-negative edges. This efficiency makes it a great choice for many real-world applications.
Okay, now let's us move on to our real-world simulation. So, as you can see in the screen, we have the application, a network routing shortest path for data packets, the emergency evacuation, fastest routes in the disaster-prone area. So this is our example topic sa ato ang in this example. So example, the path from D to C. So as you can see, the shortest path in this example is from D, E, and C, where the distance is only 6, while B, A, and C is a total of 7. So we can assume that the shortest path in this example is D, E, and C. So that is the shortest path. So for example, let's give more examples. So let's put it the emergency evacuation. Our current location is in D, then our final location is found in F. So let us find the shortest path. First, we go to D. D to A is 4. Then A to C, 3. C to F is 5. So the total of 5 is 4, 9, 12. So that's the total distance from D, A, C, and F. Next is the D, E to E to C is 4, 6. Then E to B to 8. Then B to F, that is 12. Same as the D to E, then E to G, then G to 5, to F, that is 5. So it is the shortest is D to E, then E to C, then C to B, then B to F. That is our shortest path. Now, let us look to the two cases to see how Dijkstra'S algorithm perform. The first case that we discuss is the computer routing case. The goal is to find the shortest path for data packets router 1 to router 8. That was the given example. Then the test 2 case, the emergency evacuation planning. The goal is to the quickest evacuation route for a critical point from one point to the safest zone 5. Wait evacuation time in a minute. So this is the purpose of our research paper that expressed that we will find the shortest route possible. And finally, the results and observation of our paper. Uh, Dijkstra's algorithm efficiently computes the shortest path in various scenarios. It provides it very useful in the network optimization, emergency planning, uh, or the total travel weights. This result shows Dijkstra's algorithm is reliable and effective in solving shortest path problems in real-world applications.
So next, let's evaluate the performance of Dijkstra's algorithm. We can compare how it performs when executed in parallel versus serially. We look at several metrics, including the mean time it takes to find the shortest path, the precision of the results, memory usage, and computational efficiency. For example, parallelization can be achieved using OpenMP and OpenCL, which can help improve performance under certain conditions. To thoroughly evaluate Dijkstra's algorithm, we measure its performance and on different computer configurations like dual-core and i5 processors. We also compare it with other pathfinding algorithms such as A asterisk, Bellman-Ford, and Floyd-Warshall. Our focus is on understanding the time and memory efficiency of those algorithms and their scalability as the graph size increases. The results show that due to its sequential nature, Dijkstra's algorithm is challenging to parallelize effectively. On average, parallelization provides only a 10% speed up. Despite this limitation, Dijkstra's algorithm remains reliable, moderate sized graphs, and it's practical for many real-world applications. It consistently produces accurate and efficient solutions for finding the shortest path.
Now, let's move on to algorithmic strengths. So, the extra algorithm has several strengths or advantages. It performs consistently well with the graphs that have positive weights. This makes it effective in dynamic environments, just like network routing, where it needs to find the optimal paths quickly. The algorithm deterministic nature ensures that it always finds the shortest path. Additionally, it scales when Additionally, it scales well when used with data structures just like priority queues and so on, allowing it to handle larger database or dataset efficiency and efficient. Now, let's go to the limitation and challenges. So, even though the extra algorithm has a lot of advantages or strengths, it also have a limitation on challenges. So, the extra algorithm does have some limitation, just like it can face performance bottlenecks with dense graph because of the high and computational resources required. And also inefficient with dealing with the graphs that have negative age weights, as it can handle those cases properly. Furthermore, it is not suitable for scenarios just like when the graph changes frequently on the large scale, as recalculating the shortest path can become burdensome. So let's go on to the comparative analysis. So we compare the Dijkstra algorithm to the other existing algorithm, just like a asterisk Bellman-Ford Floyd-Warshall algorithm. So as we compare this, we we conclude that this algorithm is excellent for sparse graphs with positive weights. However, for graphs with negative weights, Bellman-Ford is more efficient than the Dijkstra'S algorithm. So Bellman-Ford is a better choice. So for dense graphs, Floyd-Warshall can be more efficient, and for A asterisk is particularly useful for directed searches with a good heuristics. So when choosing an algorithm, it is more important to consider the characteristic of the graph to ensure the optimal performance or the overall efficiency of the algorithm. So, so that's all, and thank you.